Increasing and decreasing functions. So the reason why we use derivatives for graphing is because back in the day, there weren't graphing calculators to determine what a graph looked like. So they would always take the derivative of an equation, which made it easier. So a cubic graph always turned into a parabola graph always turned into a line. So derivatives are used to determine where the graph is increasing, which means it's positive, or if it's decreasing, which means that it's going down into the negative numbers. So if f prime of x is greater than 0, then the graph is increasing. If f prime of x is less than 0, then the graph is decreasing. So the derivative of the equation, if it's greater than 0, that means that the graph is increasing. If it's less than 0, then the graph is going down, it's decreasing. So we need to be able to plot these on a number line because we will be looking for the zeros of a graph. You'll notice from in the past, when doing graphing, a lot of graphs, whether it's the cubic graph or a parabola, those curves go through the x-axis. And those x-intercepts, those zeros, are really important for the graph. So how do we write these? First example says that all people younger than 15 and older than 5. So that means that 5 and 15 are not included in this. So we have open circles at 5 and 15. And in order to represent this, we use curved brackets from 5 to 15, but with the curved brackets, it means that it doesn't include the number 5 and it doesn't include the number 15. The second one, all people between the ages of 15 and 5 inclusive, which means that the number 5 and 15, those ages are included. So the circles at those points, 5 and 15, are shaded in, and since they're included, we use square brackets. All people 5 and older, which means that 5 is included, so we represent this from 5 to infinity. And infinity never ends, that's why we use the curved bracket for infinity. So here we have a cubic graph. And we want to know the intervals in which this cubic graph is increasing and decreasing. So from this cubic graph, we can kind of get an image from doing graphing in the past that this is a cubic graph that starts down and ends up. And we can use our graphing calculator to see what the graph looks like. But if we didn't have technology, what we would do is we take the derivative of the equation. So the derivative of x cubed is 3x squared. Derivative of negative 2x squared is minus 4x. We are going to factor the right-hand side of the graph of the equation to determine the zeros. So 3x squared minus 4x, if we're going to factor this, we have to take out an x. Then we're left with 3x minus 4 in brackets. So our zeros, our x-intercepts for the graph are 0 and 4/3. And we're going to plot these on a wriggle graph. In between 0 and 4/3, we're going to identify other points to check in. So I've identified -1, 1, and 2. And with these checkpoints, we're going to determine whether the graph is increasing or decreasing. And where we put those numbers into is into the derivative equation. Because from the beginning of our notes, it said that if f prime of x is greater than 0, then the graph is increasing, which means it's going up. If f prime of x is less than 0, then the graph is decreasing, which means the curve goes down. So let's substitute -1 into the derivative equation. And when we substitute -1 into our derivative, it equals 7. So since it's a positive number, you're just looking for whether it's positive or negative. It's a positive number, so that means it's increasing. So from negative infinity to 0, it's increasing. The graph is going up. When we plug in 1, we see that it's -1. So from 0 to -4, it's decreasing because we have a negative number. When we substitute 2 into the derivative equation, our answer is 4, which means that it increases from 4/3 all the way to infinity. And if we confirm this derivative graph, you can see that we get a parabola with the zeros 0 and 4/3, and you can see how it opens up. Our next equation, we want to see where the intervals on this graph is increasing. And our knowledge of graphing tells me that this is going to be a rational graph. And since the degree of the numerator is the same as the degree of the denominator, I'm going to have an asymptote at 2/3. So that's just my knowledge from previous math work in Math 12. And we may have done a little bit in calculus, but I think it was Math 12 that we did it in. So you're looking for intervals that are increasing. You're looking for where the derivative graph is positive, which means the slope of the tangent line is positive, because remember the derivative is the slope. And in order to take the derivative of f of x, we need to use the quotient rule. So we leave g, take the derivative of f, which is 2, minus, leave f and take the derivative of the denominator, which is 3, all over 3x plus 2 squared. If you're not familiar with the quotient rule, please look back in your notes or look back into a YouTube lesson on the quotient rule. Simplifying, we distribute the 2 and the 3 into the brackets, and we combine like terms. So here we have the derivative. Now in the denominator, this cannot equal 0 because we can't have 0 in the denominator. So since there aren't any zeros, it means that there's no maximum or minimum point. And our asymptote is found at -2/3. So I plot -2/3 on my wriggle graph, and I just pick points that are easy to substitute in. So we always pick nice whole numbers like 0 or -1 or 1 or 2. And in this case, I picked -1 and 1. So when I sub in these graphs into the derivative, I notice that when I substitute 1 in, it's positive. So that means it's going to increase on the right. So from -2/3 to 1, it's going to be increasing. And when I substitute -1, I get 1 as well. So that means that the graph is increasing on the left as well. And I have an asymptote at -2/3. I confirm the solution by graphing the derivative, and this is what I get. This is my result.